Hello everyone, Assalamu alaikum. Welcome to the new lecture on pharmaceutical chemistry. In this video lecture, I am going to discuss with you about the Baeyer-Villiger oxidation reaction. Baeyer-Villiger oxidation reaction is also one of the most important organic chemical reaction. This was introduced by the Adolf von Baeyer and Victor Villiger. They have first reported this reaction in the 1899. By the application of this reaction, they have caused the oxidation of the different type of ketone by using the peroxy acids or per acids as the oxidizing agents. So the per acid or peroxy acids that are used in the oxidation reaction as oxidizing agent, they have caused the oxidation of ketone, and they themselves are going to be reduced during this reaction. So we have to discuss that how the reaction mechanism of this reaction is occurring, which type of bonds are being formed and broken during this different step of the reaction. So let's check out that what is the definition and different characteristic of the Baeyer-Villiger oxidation reaction. Baeyer-Villiger oxidation reaction is basically the oxidative cleavage of carbon-carbon bond, which is adjacent to the carbonyl functional group, and by this cleavage the ketone are get converted into the esters, and cyclic ketone are converted into the esters that are commonly known as the lactones. The Baeyer-Villiger oxidation reaction is basically facilitated by the peroxy acids or per acids. The example of peroxy acids that are mostly used in the Baeyer-Villiger oxidation reaction are the metachloroperoxybenzoic acid, hydrogen peroxide, and the other trifluoroacetic acid or peroxyacetic acid. So basically Baeyer-Villiger is the oxidation reaction of the ketone, and by the oxidation reaction the ketone are getting converted into the esters. Clear? And how this oxidation is occurring, because during this reaction, in the reaction mechanism, you will observe the oxidation is causing the cleavage or breakage of carbon-carbon bond. Which carbon-carbon bond? Which is adjacent or near to the carbonyl functional group. And as this bond is broken, and the oxygen will be introduced, and in this way ketone are get converted into the esters. This oxidative cleavage is caused by the oxidizing agent that are mostly the peroxy acids. Now let's check out the different characteristics of the Baeyer-Villiger oxidation reaction. Mainly this reaction involves the oxidation cleavage of carbon-carbon bond. Means in all type of Baeyer-Villiger oxidation reaction, means which is using any type of ketone, what will happen in any type of ketone, the cleavage or breaking of carbon-carbon bond that is near to the carbonyl functional group will occur. And in this reaction will be happen by the use of the different type of oxidizing agent or the reagent molecule, like the metachloroperoxybenzoic acid, which is one of the most versatile reagent for the Baeyer-Villiger oxidation reaction, peroxyacetic acid, peroxy trifluoroacetic acid, hydrogen peroxide. Clear? So now let's check out what will happen if we are going to substitute this peroxy acid with different functional group. Like for example, if we are going to substitute these peroxy acid molecule, which are the reagent molecule, with the electron withdrawing group, then the rate of reaction will be increased, because electron withdrawing group have the negative inductive effect. They are going to withdraw the electron from peroxy acid molecule, and in this way, if such peroxy acid which have the electron withdrawing functional group attached with them are used in the Baeyer-Villiger oxidation reaction, then the rate of reaction will be more. The Baeyer-Villiger oxidation reaction are usually the ratio specific. This will depend on the type of ketone, because some ketone are symmetrical ketone, some are the unsymmetrical ketone. Symmetrical ketone are those which have the same side of R radical on both sides of carbonyl functional group, like acetone have the methyl on both sides of the carbonyl functional group. Unsymmetrical ketone are those which have the different R side chain on the both side of carbonyl functional group. Means on one side it can be the methane, on the other side aromatic side chain, or any like methyl or ethyl on other side. So they are the unsymmetrical ketone. So for the unsymmetrical ketone, the Baeyer-Villiger oxidation reaction is usually the regiospecific, means it will cause the migration of that alkyl group which will stabilize the positive charge on the oxygen, because in the reaction mechanism you will observe that positive charge will be created on the oxygen molecule, which is basically the instability parameter. So in order to stabilize it, that aldehyde radical will be shifted towards the oxygen, which have the greater positive inductive effect, because it will donate or release the electron, and in this way it will stabilize the oxygen. And so that is basically the regioselective parameter of the Baeyer-Villiger oxidation reaction. So for that we have the order, that is the migratory aptitude order. So this order will be followed this rule will be followed for unsymmetrical ketone, means the hydrogen will have greater affinity than tertiary alkyl, which have the greater than cyclohexyl, greater than secondary, greater than benzyl, greater than aryl, greater than primary, and greater than methyl. So methyl has the lowest migratory aptitude than all of these functional group on the basis of the positive inductive effect. So we can say, in other words, that the tertiary alkyl has the highest order of migratory aptitude, means it can be migrated at the greater extent than any of these functional group if present on other side of the R radical. Clear? So this rule will be followed in the third step of the Baeyer-Villiger oxidation reaction, which we will discuss in the upcoming slide in the reaction mechanism. Baeyer-Villiger oxidation reaction is usually the second order reaction, and second order as it is the second order reaction, so the rate determining step will be not the first step, it will be any of the step. So in the Baeyer-Villiger oxidation reaction, usually the rate determining step, which is the slowest step, we know that rate determining is that step which is the slow step of the reaction. So in Baeyer-Villiger oxidation, rate determining step is that step in which the migration of the alkyl radical RR is occurring towards the oxygen. The migration or the rearrangement is occurring in the concentrated step or the single step, and due to which the configuration of the migrating chiral substituent has been retained. So that's why it is a concentrate or single step, that reaction single step in which the migration is occurring. Aldehyde can also undergo through the Baeyer-Villiger oxidation reaction, but when aldehyde undergo through the Baeyer-Villiger oxidation, they will get converted into the carboxylic acid, and they can also get converted into the formates, but the formates are usually the unstable, and due to which they can undergo further through the hydrolysis reaction and get converted into the alcohol. So in case of aldehyde, the migratory aptitude will be hydrogen, which is written here. Hydrogen will have the greater migratory, and that's why they can be converted into the corresponding carboxylic acid. Now let's check out the general reaction mechanism and the detail of the different step of reaction reaction step that is occurring in the Baeyer-Villiger oxidation. So we observe that ketone is reacting with the per acids, and it will get converted into ester. This is the general formula for ester, and this is the acetic acid, because in this we have used the per acetic acid as our per acid. So in the lecture of basic organic chemical reaction, we have learned that reactant is basically of two types. One is the substrate molecule, other is the reagent. So in this Baeyer-Villiger oxidation, ketone is acting as a substrate molecule. Ketone and aldehyde in this second reaction is acting as the substrate molecule, and peroxy acid will be our reagent molecule. So this reagent will take this substrate, and that's how it will get converted into the ester. And in the second reaction is for the aldehyde. Aldehyde, when react with peroxy acid, it will get converted into the carboxylic acid. The third reaction is for the cyclic ketone, that is going to react with the peroxyacetic acid and get converted into the caprolactone, that is the product of the cyclopentanone, that is the ketone. Over here the reaction for the acetone is shown, and it is going to react with the peracetic acid, and it will get converted into the methyl acetate and the acetic acid. So now let's discuss or learn about the detail of the reaction mechanism for the Baeyer-Villiger oxidation reaction, that what are the different steps for the Baeyer-Villiger oxidation reaction, how the ketone is getting converted into the esters. So it is basically, this conversion is basically occurring by the help of oxidizing agent, that are the peroxy acids. Okay, so now we have to check out that how this conversion is taking place. What are the different steps of Baeyer-Villiger oxidation? There are the 4 different steps in which the ketone are getting converted into their final product, that is the ester. So in the first step, basically the protonation of carbonyl oxygen of the ketone will occur. This protonation will caused by the peroxy acid proton, and by this the ketone will get converted into the protonated ketone and percarboxylate ion. Clear? So this will cause the protonated ketone as the more nucleophilic. So how this protonated ketone is formed? We know oxygen have the lone pair of electron. Clear? And this lone pair of electron, when comes in contact with the peroxy acid, so the proton from the peroxy acid will attack the lone pair of electron of oxygen, and it will get attached over here, and that's how the ketone will get converted into the protonated ketone, and the remaining part of peroxy acid will get converted into the percarboxylate ion, which have the negative charge, because this negative charge is caused by the deprotonation, because proton or hydrogen have been removed from here and get attached at this type of ketone. And now we may observe this oxygen has now positive charge due to the gain of this proton from this. So in the next step you may observe this protonated ketone and percarboxylate will react. So now in the next step you may observe this is the protonated ketone in which oxygen has the positive charge, which is usually the unstable parameter. So this bond, double bond, will break down and it will get shifted toward this oxygen and to stabilize this positive charge, and now this carbon will have the positive charge, which will be attacked by the negative charge oxygen of the percarboxylate ion, and in this way an intermediate is formed, that is the Krieg intermediate. This is the Krieg intermediate, and this you may observe that carbon oxygen have the single bond. This is occurring why? Because this bond has been broken in order to stabilize the positive charge on oxygen, and in addition this intermediate has this side, on this side it has the percarboxylate, this has the percarboxylate chain. Clear? So in this reaction what is basically occurring, the carbonyl carbon is being attacked by the electron from the percarboxylate, because because of the breaking of the carbonyl oxygen double bond, and this carbon has now positive charge, due to which it can easily be attacked by this negative charge oxygen. So that's why it is being converted into the intermediate. So now let's check out the third step, which is the most important step of the Baeyer-Villiger oxidation. In this third step, this Krieg intermediate will convert it into the protonated ester and carboxylate ion. Now how this conversion is taking place? So this is important step. We know that oxygen have the lone pair of electron. These lone pair of electron will get shift and will form the double bond over here. So over here carbon oxygen double bond is formed, and again hydroxyl functional group is present. So as these lone pair of electron is moving here, so oxygen will again have the positive charge. Clear? The other important thing to learn or understand here is you may observe that in this intermediate we have the oxygen bond, which is weakest bond. So this bond will be easily break down, and in this way the carboxylate ion will be formed, and this remaining and oxygen will have again the positive charge due to the breakage of this bond or shifting of this bond at this position. So in this way oxygen have positive charge. So in order to stabilize the positive charge, one of these R radical will be shifted to this oxygen, and that's how this will get converted into the protonated ester. Now question arises, which R radical among these R1, R2 will be shifted to oxygen. Over here, the rule of migratory aptitude will be followed. In migratory aptitude, which we have learned in the characteristics of the Baeyer-Villiger oxidation, that unsymmetrical ketone which have the different R radical. Clear? So we have learned here that the tertiary alkyl have the greater migratory aptitude or affinity than cyclohexyl, which have greater than secondary, greater than benzyl, greater than aryl alkyl. Methyl is the lowest. So for example, on one side we have the tertiary alkyl, on other side we have the methyl. So which will be shifted or migrated? Obviously tertiary alkyl will be migrated towards oxygen. So this rule will be followed in the third step, that is the most important step of the Baeyer-Villiger oxidation, in which the formation of protonated ester will be take place. So in this way, protonated ester and carboxylate ion will be formed. In protonated ester, you may observe that oxygen has the positive charge and also it has the proton. So that is also an unstable, so it must be converted into the our desired ester molecule. How it will be converted? In the final step, the electron from the carboxylate oxygen, which have the negative charge, will attack the proton of the protonated ester, and in this way they will get converted into the corresponding carboxylic acid, and this bond will be shifted toward oxygen in order to stabilize its positive charge. Clear? So ester formation will take place in this way. So these were the different steps for the Baeyer-Villiger oxidation. In the first step, we have learned that the protonation of the carbonyl functional group occurring. In the second step, Krieg intermediate formation is occurring due to the nucleophilic attack on carbonyl carbon by the percarboxylate ion. In the third step, that was the most important step, protonated ester formation is occurring, and in this third step, the rule of migratory aptitude or the criteria affinity was being followed. So this was the most important, and in the final step, protonated ester was converted into the ester due to the deprotonation, because deprotonation is how occurring, because this proton is being removed and it was being again by the electron from the carboxylate and get converted into carboxylic acid and ester. So this was the detail about the reaction mechanism of the Baeyer-Villiger oxidation. I hope you have understand each and every step, and now you have to follow all these steps, and you have to draw by your own in your copy the detailed reaction mechanism for all of these compounds. Like you have to draw these 4-step reaction mechanism for the cyclopentanone and get how this will get converted into this caprolactone product. You have to follow all these 4 steps. Clear? And in the same way, you have to follow the reaction mechanism and draw the reaction mechanism for this acetone molecule when reacted with the peracetic acid, and how it will get converted into this product. You have to draw the desired reaction mechanism 4-step. And in the same way, you have to draw the reaction mechanism for these different examples. Like in this example, acetophenone, that is one of the aromatic ketone, when reacted with trifluoroperacetic acid, it will get converted into the methyl benzoate. But over here, this is wrong, that oxygen is placed here. Oxygen will come at this position, because you may observe that this is the carbonyl carbon. On one side, it is attached with the methyl, on other side it is attached with the benzene ring, that is the phenyl radical. Also in this way, we have learned in the migratory aptitude rule that that R radical will be shifted toward oxygen, which have the greater positive inductive effect, and we have observed that methyl is greater than the phenyl radical has the greater migratory aptitude or positive inductive effect or greater affinity to stabilize positive charge of oxygen than the methyl. So in this way, oxygen will come in here and methyl benzoate ion will be formed. So you have to draw the detailed reaction mechanism for this acetophenone and for ketone as well. This is the cyclohexanone. When reacted with peracetic acid, it will get converted into the caprolactone. So oxygen will come at this because this is the carbon-carbon bond adjacent to this carbonyl functional group. and this one is also the butanone, and in this you may observe the carbonyl on one side is the methyl, on other side it is the ethyl. So ethyl is basically the secondary carbon. Why? Because this carbon is being on one side being bonded with carbonyl, and on other side it is bonded with the methyl, means it is acting as secondary. And we have learned that the secondary alkyl have the greater migratory aptitude affinity than the primary or the methyl group. So in this way oxygen will come at this position and we have this major product. So you have to draw the desired 4-step detailed reaction mechanism for all of these ketone, including this cyclohexyl ethanone, which when reacted with metachloroperbenzoic acid get converted into the cyclohexyl acetate. This is the product. This is the ester molecule product of this reaction. In this reaction you have observed that oxygen is being introduced at this place. Why not at this position? Because this is the carbonyl functional group, this is the cyclohexyl on one side, this is methyl on other side, and we have learned in the migratory aptitude rule that the cyclohexyl have greater affinity migratory aptitude than the methyl. So that's why oxygen will come at this carbon bond, and this will be cleaved and oxygen will come here. So you have to draw the detailed mechanism for all of these reaction, your copy for your practice, because this will be part of your exams. So this is most important. So now let's check out the applications of Baeyer-Villiger oxidation. Baeyer-Villiger oxidation is important. Why? Because it is useful for the preparation of esters, preparation of carboxylic acid, synthesis of lactones. The lactones are basically the part of are responsible for the flavors and fragrance of the different fruits, different fermented and unfermented dietary products. So, and the esters and carboxylic acids are used in the synthesis of various pharmaceutical agents, drugs, medicines, and the other essential compounds, organic compounds that will be further utilized in the synthesis of the drug. So this was all about the detail of the Baeyer-Villiger oxidation reaction, from its basics, from its characteristics, and the detailed reaction mechanism. I hope you have understand each and every detail of it. Now the most important part, the quiz are given in the description section. You have to attempt the quiz in the comment. Thank you very much. Allah Hafiz.